out your notebook. What I would say, though, is my first few slides, I don't really need you to write down anything. So my first few slides of text, I'm just going to have things that I'm going to talk about so you can listen. And at one point, I'm going to tell you, hey, this is the one thing I want you to write down that's actually important. So we don't have to write down a lot of stuff in this first batch of notes. Plus, not to get you overly excited, but the second batch of notes, I'm going to give you one of the greatest gifts a chemistry teacher could give students today. It's going to be great. Connor, I can see the excitement on your face. Okay, so again, we're not writing any of this down because we don't need to write any of this down because I am not going to ask you on a test to find what an oxidation number is. And we are not in the business of memorizing and regurgitating out definitions in this class. So, on this slide, why are we working with oxidation numbers? An oxidation number is kind of a hypothetical of how many electrons do you have around an element. Now, it's not saying like gold, for example, it's element 79. It's not going to give an oxidation number of 79. Most things that don't have a charge, we would just give it an oxidation number of 0. Hey, it's neutral. There's no difference. But then whether something has more or less electrons than it normally would, we would give it a number associated with that. Sometimes that's in an ionic compound. So ionic compounds have things that gain and lose electrons, so that's an easier one to keep track of. Some things, it's a little trickier. It's in a covalent compound. So covalent isn't about gaining and losing electrons, it's about bonding. But those oxidation numbers can even give an indication of how it's bonding. So again, there's going to be little tiny numbers that we're going to be looking at, thinking about start to finish, how does it change? That's really the goal for today. Okay, now if I look at my second slide, the only thing I want you to write down is the very bottom point that I have here. So I'll start by explaining what I have on the top here, but the bottom point is what we want you to know from this first batch of notes. And that's actually the only thing you're going to write down at all for this first batch of notes. So, why do we learn oxidation numbers? They're already on your periodic table, ladies and gentlemen. We just got to show you how to use it. Sometimes we simplified and didn't say that they were oxidation numbers, but we have to go over that. What you will see, as my first bullet point says, is a lot of the reactions that we've already done this year, they fall into the category of oxidation or reduction reactions. We've just never said that they were. Remember the reaction type we just got done with, acid-base? Kind of like double displacement? Well, you're going to see oxidation reduction. That synthesis reaction might be a redox, or that single displacement might be. So when I say this is a new part of our reaction unit, we're not going to be throwing really weird reactions at you all of a sudden. We're going to be taking reactions that you're already familiar with and showing you how they've been defined as an oxidation reduction reaction. And that gets me to the second point. I'm sick of saying oxidation reduction reaction. We usually just call them redox reactions. A little quicker way to say it, so then we don't have to say as much. Again, in chemistry, we abbreviate the word mole, M-O-L, to save us a little time. So we're going to abbreviate oxidation reduction and call it a redox reaction. The one thing I asked you to write down, and what does this have to do with reactions, is a lot of reactions occur due to a gaining or losing of electrons. And in an oxidation reduction or redox reaction, we're going to determine what thing gained electrons, what thing lost electrons. Now, what I can tell you about redox chemistry is there's a ton of applications out there. We, unfortunately, don't really get into much of that at all. So I can speak from an AP chemistry standpoint. Anything dealing with batteries and electrical chemistry is all redox chemistry. So that's something that we cover a fair amount in AP chemistry. If you were to take like AP Bio at some point, they're going to talk about cellular respiration in a lot more detail than you probably talked about it in biology as a freshman. And they're going to bring up redox chemistry at that point. So Ms. Kirker will talk about that there as well. Not every type of chemical reaction is dealing with something gaining and losing electrons, but a lot of them are. And that's why some of the reactions that we've already covered fall into this category. So, here's a periodic table, zoom in. What we taught you first semester is if you look at the tiny little numbers directly above the symbol, it gives you what we said at the time, the charge. If it was, for example, an anion, oxygen's a -2. But then some periodic tables also show oxygen with a -1. And now we got to think, why is that? Oxygen can only have one charge if it's an anion. Or maybe a better example is if we looked at sulfur on the periodic table, it has a whole bunch of little numbers directly above it. There's a +2, a +4, a +6, and a -2. Well, the -2, just like oxygen, would be its ionic charge. But all those other little numbers, the +2, the +4, and the +6, those are actually referring to oxidation numbers. So the ionic charge and oxidation numbers are all grouped together and put on your periodic table. And actually, when you look at your periodic table and it gives you the key on the bottom left-hand corner, it says that these are the oxidation numbers when it gives you what does this number mean. We've never defined them as that before because there is a difference between an oxidation number and an ionic charge. An ionic charge can be an oxidation number, however, the reverse doesn't necessarily work. So we have to go over how to use our periodic table today and a few of the rules that we have to use as well to figure this out. Now those rules are on a sheet that you picked up on the way in that says rules for assigning oxidation numbers. So we wrote down one statement so far about redox. Let's put away our notes and get out that rule sheet that you picked up on the way in. Now you can see on the top of this rule sheet that there are 8 rules. We don't really have you memorize them, but at the same time we do need to be aware of them. By the way, instead of just getting out that rule sheet, how about we get out our periodic table as well? Maybe even our polyatomic ion sheet. What? Okay, so as we're getting organized, I'll start to read down the rules on that rule sheet. The first rule I actually already mentioned. If an element is by itself, and this includes diatomics, its oxidation number is 0. Again, it's neutral, so we give it a 0 oxidation number. However, if you are bonded to something else, either ionically or covalently, now you have an oxidation number, and usually it's going to be something other than 0. So for example, number 2 says the oxidation number for an ion is its charge. So if we had iron +2 in a problem, +2 would be its oxidation number. Okay, so that should hopefully be simple. When we have ionic compounds, whatever the ion's charge is, that is its oxidation number. And number 3 goes over other examples of that. Remember your group 1, your alkali metals, those are all a +1 for an oxidation number. Your group 2, your alkaline earth metals, those are all a +2. This is just like ionic charges until we get to things that aren't ionic. Number 4, the rule is that fluorine's always -1. Number 5, hydrogen is a +1 unless it's bonded to a metal, then it's a -1. Rule number 6, oxygen's usually a -2. However, there are a couple of exceptions that it shows. Rule number 7, a more electronegative element will have an oxidation number equal to its charge as an ion. And finally, rule number 8 is the one that we're going to use the most. If you have a compound, all of the oxidation numbers combined would equal 0. So we're kind of like balancing charges in an ionic compound. However, technically, we're not always doing ionic compounds. That being said, if you want to treat it that way to make life, easier up in your head, just do it for this, okay? So what might help is if we do the 2 problems on the bottom of this sheet. The first one is KClO3. What typically is going to happen is we give you a compound, and some of the elements you can look on your periodic table, and there's only one option for it. So you know what its oxidation number is right away. It makes life simple. However, usually there's going to be at least one thing in the compound that you have to figure out a little bit. Now, when I said solution stoichiometry is the only math that we have in this unit, there's going to be, a tiny bit of math, if you want to call this math, that we're about to do. Do we know potassium's oxidation number when we look at our periodic table? What is its oxidation number? What's the only number directly above your K? +1. So, that's simple. Does chlorine have only one number directly above it? No, it has a whole bunch of little numbers above it, right? So again, we're looking at chlorine on our periodic table directly above it. Whole bunch of numbers. Whole bunch of possible oxidative states. Because we don't know chlorine, I want to skip it. Let's move to oxygen. Do we know oxygen's oxidation number? The -2, isn't it? Oxygen is almost always a -2. Again, that rule number 6 up above gives you the 2 examples it isn't. Most of the time, you only have to deal with that. Okay, so we know potassium's a +1. We know oxygen's a -2. We need to figure out the chlorine. And we're going to do a little math to figure it out. And then we can check our periodic table to see, is that one of the possibilities? Now, I'll be honest with you. The periodic table shows the most common oxidative states. There are once in a while examples of things that aren't on the periodic table, but usually this is a good way to check your answer. How we figure out chlorine is there is one potassium as a +1. There are 3 oxygens and each are a -2. So I'm going to take -2 times 3 to get -6. 1 plus whatever my chlorine is, plus a -6, has to equal 0 because the oxidation numbers all balance out. So this is a little bit of math, I suppose. So what must chlorine be in order to get this to balance out? +5. When I report oxidation numbers, I usually just write it right above the symbol. The one thing that sometimes throws off students, oxygen is a -2. We're not going to call oxygen a -6 because 3 oxygens gave us the -6. We need to report the oxidation number for each individual atom. So what you do, you look on your periodic table. If there's only one number above it, write it down. Just like you would for a charge, that's the oxidation number. Then, if there's one thing you have to figure out, you do a little bit of math like I showed here. The next one below is a little bit more difficult. Ammonium nitrate is NH4 NO3. Which element will we know right away? Oxygen, we will. Oxygen's always a -2, like we said last time. Hydrogen we should know as well. Hydrogen is almost always a +1. The only time it isn't if it's bonded to a metal. Nitrogen's not a metal. Okay. This one I picked specifically because it's a little bit trickier. And what I mean by that is I have 2 nitrogens left over, and nitrogen has a lot of options. So we need to figure out each nitrogen. However, the 2 nitrogens aren't necessarily the same oxidation number. This is a polyatomic ion, ammonium. Ammonium is a +1 polyatomic ion. This is a polyatomic ion, nitrate. Nitrate's a -1 polyatomic ion. The oxidation numbers of everything within a compound will equal 0 if that compound's neutral. If, however, we broke it down into its parts, and we know hydrogen's a +1, +1 times 4 is a +4. Nitrogen +4 would equal the charge of the polyatomic ion. So if we are trying to have it solve for something that isn't neutral, it's going to equal its charge. That's why, even though NH4 is not an ionic compound, it's two nonmetals covalently bonded together, we can still kind of think of this as charges balancing out. They're either going to balance to be neutral because the thing is neutral, or they're going to balance out to the charge of the polyatomic ion. Either way, a little bit of math here should tell us that nitrogen is what? Something plus 4 equals plus 1? -3. Let's do the same thing with the nitrate. We know the oxygen in nitrate's -2 times 3 is -6. The nitrogen -6 will equal a -1. +5. So if I go back up to the top, keep with my green here. I picked this particular example to show you, even though it's nitrogen, nitrogen could have two different oxidative states. How nitrogen bonds in ammonia is different than how it bonds in the nitrate polyatomic ion. Oxidation numbers are a general representation to show how that bonding occurs, how many electrons are around it at a given point. Jordan?
So if we have two polyatomic ions, should we always like split them up?
I would split it up, yeah. Unless you only had one thing that you didn't know. Because if you know everything except for one thing, then just set it equal to 0.